Okay, SI4. So we have a vector field given to us. We have a surface given to us. We want to compute the flux. Let's draw a picture of the surface first. So X is this, okay, it's a paraboloid. So I'm going to let you guys play the Chapter 2 or Chapter 3 games. I forgot, Chapter 2, I guess. But I claim that what this looks like is there's a circle of radius 2 in the YZ plane, and then this is a sort of a paraboloid that extends backwards on the Z-axis like that. On the X-axis like that. So does that make sense to everybody? I'll let you guys persuade yourselves that this is what it looks like. Okay. So this intersects back there. Okay, so now a big glowing hint on this problem is that we're in the section on surface independence. But even if we hadn't noticed that, one thing we've already talked about is the idea that when you're asked to compute a flux, go ahead and compute the divergence of your vector field. It just might be handy. And so let's do that here. Let's compute the divergence of the vector field. And let's see here. The x partial of the first component is 2x plus 5. And then the y partial of the second component is minus 2x. Oh, that's cool. And then the z partial of the third component is minus 5. So everything cancels and you get 0. And this tells you a couple of things. On the one hand, it tells you that there is an anticurl, but we don't know how to compute anticurls, and so that's not that useful here. But more importantly, what this tells us is that this vector field F is surface independent. So that means that after having gone to the trouble to draw a picture of the surface, I'm now going to basically ignore it, caring instead only about its boundary curve. And I'm just going to find any surface that I feel like that has that same boundary curve. Oh, let's think about orientations, by the way. So the original surface was oriented in the negative x direction, so oriented that way. And that means that the boundary curve is oriented that way. Again, you got to think about the thumb and the way your fingers curl around, etc. And that means that when I find another surface that has that curve as its boundary, I just have to orient it in the appropriate way. And so I'm going to, of course, not surprisingly, pick this disk in the YZ plane. It's nice and convenient. And I have to orient it in the negative x direction. Oh, this pen really is dying, isn't it? The negative x direction in order for the orientation to match up with the boundary. That's right. So the rule is that the old surface and the new surface have to have the same boundary, but that's in an oriented sense, right? Okay. So they have to have the same oriented boundary. So since this was an oriented surface, its boundary is an oriented curve, and you have to pick an oriented surface that has the same oriented curve as its boundary.
See, I was getting confused when I was reading the art, just reading back over surface independence.
Yeah.
Just the full chapter.
Yeah.
The reason why it's set in backwards at the boundaries.
Well, that's the thing. It looks backwards, but they're actually not backwards. So now, again, you might look at these two surfaces and say, hey, these are kind of backwards because one of them is pointing sort of outward and one of them is pointing sort of inward, and it feels backwards, but it's not. They're the same in the sense that their boundaries have the exact same orientation. Okay. You see what I'm saying? Now, they are opposite. If you were to look at the sort of bullet-shaped little solid on the inside there, then as part of the boundary of that solid, that one's positive, that one's negative.
Oh, the boundary of the solid. Okay.
Yeah, that's the thing. It's like they have boundary, they are boundary. I mean, there's three different columns involved in this. We have the three-dimensional solid, the two-dimensional surfaces, and the one-dimensional boundary curve. So there's two different boundary operations involved. And so that's right. I mean, so in the sense of one of those, in the sense of three-dimensional boundaries being two-dimensional surfaces, these are what you might want to be tempted to call opposite. But in the sense of two-dimensional surfaces having one-dimensional boundary curves, these are the same orientation because they have the same orientation on their boundary. Does that make sense?
That makes perfect sense.
Fantastic. Okay.
Do you mind if I just take
Yeah, these are all yours. Go ahead. No problem.
Head out, so.
Yeah, sure. No worries. Go ahead. Okay, so finishing up, this is surface independent. We've picked a new surface here, and so I'm going to compute the flux by using that new surface that I'll call, let's see what I'm going to call that. Okay, I'm going to use green here again. That surface I'll call D for disk. So I have that. Now you got to parameterize the disk, etc. But one really nice thing you notice is that on this disk, on the whole disk, x is equal to 0. Right? Because I've cleverly chosen that to be in that YZ plane. So since x is equal to 0, when you look at your vector field, it simplifies dramatically. The vector field becomes just, well, let's see, negative YZ 6. And then I still have this annoying e to the y minus 5z thing. All right, so that's not awesome, but anyway, it's a little improvement. More good news, though. I can rewrite what that ds vector is in terms of its unit normal vector. The unit normal vector is easy to write down because there it is. There's the unit normal vector. It's just pointing in the backwards x direction, right? By well, it's backwards because of the orientation, but it's so negative 1, 0, 0. So sure, that's a little ugly, but who cares? I'm multiplying it by 0. And why am I multiplying it by 0? Because I have a nice normal vector. I have a nice normal vector because I chose a nice surface, which I was allowed to do because the vector field was surface independent, which I detected because of the divergence being 0. So that's the value of doing this. So the reason you want to take that divergence to see if it may or may not be 0 is because it allows all sorts of good stuff to happen in your calculation. Does that make sense? Yeah. So, okay, finishing up now, we just have a double integral over this disk of yz ds scalar. And I claim that there's a couple different ways you can attack this integral. It's over this disk in the yz plane. And for one thing, I note that the disk is symmetric. This has odd symmetry through a couple of different choices of reflections. And so the integral is equal to 0. Or you could parameterize and solve by more direct techniques, but I like the symmetry argument. So I'm going to let you fill in these blanks here. So, why is this equal to 0? Does that make sense?
Yeah.
Okay. Is everybody good? Okay.
Could I have taken a different take by using the G, which is called
The G. Oh, you mean the anti-curl? Yeah, I mean that's one thing you could do that conceivably, but then you have to find the anti-curl. That's the problem.
Yeah.
And that's really hard. I haven't shown you any techniques for how to compute anti-curls. And in the case of this vector field, I think it'd be hard. So I think it would be a highly undesirable way to do the problem. Yeah, but absolutely. I mean, hypothetically, if somehow you could intuit or somehow find the anti-curl, then sure, you could rewrite this flux integral as a line integral over this curve of that anti-curl, and sure, that'd be a fine way to do it. It's not going to be that useful in this case. It's one of the bummers about Stokes's curl theorem is that it's so hard to find the anti-curl.